We continue our discussion now. This is the third lecture on photolithography. We just discussed that after the barrier layer is up there. So, now what we are talking about this particular stage, where we have started off with a silicon wafer. P type is, again I will repeat, this is just an example that I am giving, it is not mandatory. So, now you have the oxide layer, the barrier layer. See, I am not even giving you numbers like what should be the typical thickness of the oxide layer and things like that, because I do not think that these are important details for you to learn. Just check out in the net what are the typical thicknesses, under what condition you grow what thickness, and what is the processing condition. Just give a brief idea. I mean, what is the temperature, how long you grow, what is the oxygen flow rate. Please do not worry about these things, because these are absolutely trivial things and you can always check out a manual or in the internet about these numbers. It is important to know the process, and that is generically the process, and that is exactly what we are doing. So, after the oxide layer is there, what are the mandatory requirements? So, what is going to come up is the PR layer, the photoresist layer is going to be coated on this oxide layer. And as a run up or as a preparation for that, first thing that you need to do is you need to remove any moisture, and then as I mentioned that you can also do bit of priming, that is you coat the oxide layer with a layer of some material, some chemical that enhances adhesion between the photoresist and the oxide. Once that is done, next step is you actually would like to coat the photoresist layer, and this is done by a method which is by a technique that is known as spin coating. So, what is done? It is a very widely popular technique now. You dilute the photoresist in a solvent and you dispense some amount of this solvent on the wafer or this barrier coated wafer on which you would like to deposit the photoresist layer. You typically have arrangements of holding the, there is a chuck in which over which you place the silicon wafer, and on which you would like to dispense the solvent, and then but these are again unimportant details, we are least bothered. You should be worried about what happens, and then you rotate it at a very high RPM, and then as a result of that what happens is that initially dispensed drop, you might have dispensed it over the entire substrate or you might have dispensed it at the center. Because of this rotation, there is a centripetal force and the drop meniscus starts to spread. Why you rotate? You rotate essentially to overcome the limitation of the finite contact angle that might get generated due to Young's configuration. If you remember, I told that these days it is possible to create films on non-wettable surface, and this is one such example. So, what I mean to say that even suppose this is your wafer and you dispense your solvent solution which let us say makes a finite contact angle, and now since you know Young's equation, this you know that this corresponds to a partially wetting configuration, it is not a fully wetting configuration, but you would like to have a film that covers the entire wafer surface. So, what you do? You would like to spread this drop. How do you do that? You need to apply some force so that it can overcome the balance in the horizontal components of the surface tension along the contact line, and that is very conveniently done by applying this rotation, which in the form of the centripetal force actually leads to sort of spreading of this liquid drop or the liquid solution drop, initially dispensed solution drop. But then there are several things, several additional things that happens. There is no guarantee that it will spread only up to the edge, and therefore beyond that it will not spread, and that is exactly the case. So, as you start rotating, as the meniscus reaches the outer periphery, a significant amount of the solution is actually thrown out, it is wasted. Second thing is, you typically would use a solvent that evaporates rather fast. So, what is the rationale? That you spread the solution layer over the entire surface, and simultaneously while the substrate is still rotating on the spin coater, you want your solvent to evaporate away. So, what does it mean? What it would lead to is that eventually as the solvent evaporates away, the solute, and in this case the photoresist, makes a uniform and a very thin layer over the entire surface. This is in a nutshell what is spin coating. There are whole lot of issues associated with spin coating. So, there can be different stages. For example, the initial stage is the spin deposition. Then you spin up, you can see that the meniscus is sort of traveling towards the periphery because of this outward centripetal force. You can see that some portion of the solution is thrown out. Often this is referred to as the splash drainage or the splashing phenomena, and then towards the later stage of spin coating, it is entirely dominated by evaporation of the very important, it is the evaporation of the solvent while it is still rotating, and as a result the solvent goes away. So, irrespective of the wettability of the substrate, the solute covers the substrate uniformly. That is one of the real marvelous things of spin coating. Of course, under appropriate condition you can achieve two more things. You can get extraordinarily smooth films by spin coating on a smooth surface. Spin coating on a non-smooth or a rough surface or a non-homogeneous surface or a pattern surface itself is a matter of big research, and I intend to spend some time on that towards the end of this particular course when you are more mature to grasp the advanced issues. So, one of the thing is that you get extraordinarily smooth surface, and the second thing is that you can also create very thin films. In fact, by spin coating, films with thickness down to 10 nanometer can be routinely achieved under appropriate conditions. So, for a given substrate size, what are the parameters? Again, please do not try to remember what is the concentration, this and that, that is not needed, but what are the parameters that affect, that influence the film thickness by in spin coating. So, this is an important issue. There are some relations like this, how thickness varies with this and that. These are mostly extremely empirical data driven relations, and they often consider as some sort of a steady uniform rate of evaporation, which you now know is not the case because spin coating actually has different regimes. So, I will ask you to stay away from these type of relations. Of course, they are used and they act as a good guide at the first instant in certain places. There are certain additional issues which I will touch upon very briefly, but more importantly, the critical parameters that influence the thickness in spin coating, of course, is the spin speed, the RPM, and you can of course understand higher is the RPM, you are going to get a thinner film, because higher is the RPM, faster is the meniscus going to reach the outer periphery of the substrate, and therefore, the proportion of splash drainage or the splashing is going to be higher. Therefore, higher spin speed leads to lower film thickness. The second thing is, of course, the dispense drop volume. As you increase the dispense drop volume, you are in fact adding more amount of solvent, more amount of solute, and therefore, you are expected to get a thicker film. Again, choice of solvent is a very important parameter. more than the film thickness, whether the roughness of the dispense film depends a lot on the choice of the solvent, because if you take a solvent like THF which evaporates away very rapidly, you often do not get a very smooth film, you get a bumpy film. But if you take something like toluene which has much slower rate of evaporation because the vapor pressure is low, you often tend to get very, very smooth films. Of course, duration of spinning is another important parameter. You definitely not like to stop spinning at a condition when the solvent, when the film is still adequately wet, there is still a significant amount of solvent present, simply because of the fact that if your substrate is non-wettable and you have adequate amount of solvent, that the viscosity of the film is low, then there is possibility that the solution layer might retract back on the film surface and you may not get a uniform coverage. And of course, the ambient condition, this in fact is often neglected, but is a very important parameter, because ultimately obtaining the film in spin coating depends on evaporation, because you are going to get the film of the solute, and for that, while the spinning process is going on, your solvent must evaporate away, and the rate of evaporation of the solvent depends significantly on the relative humidity. So, if you have a highly humid situation, the rate of evaporation will reduce, and then it is like, let me put it like this, that if you are not controlling the ambient environment, reproducibility of your film thickness under identical coating conditions is going to be a critical issue, which often can hinder your performance. So, these are sort of some of the critical parameters. In fact, I would like to just highlight one very interesting aspect of spin coating. Many people tend to confuse that as soon as you start rotating, the solute starts to deposit or the film deposition starts. In fact, that is not the case. You typically start off with a very dilute solution. You deliberately take a dilute solution so that the viscosity is low. Because if the viscosity is not low, even despite of your applying significant amount of centripetal force, the drop may not spread uniformly. You might have additional roughness and things like that. So, you typically like to start with a very dilute solution, very, very dilute. So, one typically spin coats with 1% or 5% weight by weight solutions of the solute in a specific solvent. And so, after the splash drainage and whatever, you have a layer, in fact, the transparency also shows that you have a regime when you have a pretty smooth solution layer, but it is still pretty rich in the solution content, right. And what happens is the solution continuously evaporates away. Therefore, within this regime, the concentration of the solvent of the solute progressively goes up. And now it is very important to understand that you have actually taken a solvent which dissolves the solute. So, why should the solute deposit on the substrate? Well, the solute will start to deposit on the substrate only when the intrinsic concentration of the solute matches the saturation concentration. So, due to gradual evaporation of the solvent, what you need to understand is that the concentration of the solute is continuously changing, and please understand and remember forever that deposition in spin coating starts only when the intrinsic concentration of the solute in this solution layer sort of matches the saturation concentration. So, many people have this confusion that as soon as you start rotating, deposition starts to take place, but this is not the case. And since this is not the case, this is where the duration of spinning becomes very, very important. So, you might actually have to wait for a really few seconds before your deposition starts, and you do not want to hasten that you sort of spin coat for a very short duration, you might not get a uniform film at all. Please remember that even when you think that your solvent has fully evaporated, often one finds that about 15 to 20% solvent remains entrapped in a spin coated film. This effect is more pronounced in polymers because you have long chain molecules and they remain in an entangled state, and due to capillary effect and capillary adhesion and things like that, a lot of solvent molecules remains entrapped within these cages. So, you essentially, and that is something that we are going to immediately talk, we need to, even after your spin coating process is over, you need to worry about this remnant solvent. Okay. So, and we have been hearing about this particular term when we were discussing about resist processing, and that is exactly what soft baking does. So, as I just mentioned, that even after spin coating, about 10 to 20%, I just wrote 15 to 25%, these are all very debatable numbers, and there are techniques to measure it, but it is not that easy, you need to understand. So, there are about 10 to 20% of solvent that remains entrapped within a spin coated film. This remnant solvent needs to be removed. Why this needs to be removed? Because your photoresist is going to be subsequently exposed to UV, right, of course through a mask. And please understand what you expect in the subsequent step to happen. You actually expect that the photoresist layer will change its property upon UV exposure, but please do not forget that only photoresist has the sensitizer, and therefore, it will change its property upon UV exposure. But if the photoresist film contains solvent, the solvent does not change property irrespective of whether it is in the zone where it is exposed to UV light or not. And therefore, if you expose a solvent containing photoresist film, your exposure, even after exposure, the smearing, there will be significant smearing, because the solvent does not respond to the UV exposure, only the photoresist responds to. Therefore, what you would like to have? You would like to have a completely solvent free pure photoresist film, which will be used for exposure under the mask, and that is exactly what is done during the soft baking step, which improves adhesion, uniformity, etch resistance, line width control, and whatever the absorbance of the characteristics of the photoresist. But primary thing what it does, this is done at 90 to 110 degrees centigrade. Primary thing what it ensures is that it makes the photoresist layer photosensitive, and that is done by removal of the remnant solvent. Once the photoresist layer is ready, now according to the schematic we have used, it is now ready to be placed under the mask, and that is why we need to worry a bit about the structure of the mask. I have already told you how a mask is made. In fact, a mask contains is a piece of, let us say, a block of quartz or a block which is partially or at certain locations following the patterns you would like to create on your photoresist layer. It is transparent to UV light, and other locations it is opaque. So, here you can see there is a mask. So, these areas it is opaque to UV light, so no light passes, and these areas it allows the light to pass. How do you make a mask? You, as I already mentioned, you typically take a pure quartz glass plate. Why you take a pure quartz glass plate? Because pure quartz glass plate is transparent to UV light, that is a very, very important thing. But what you actually start off is with a chromium coated quartz plate, and depending on the patterns you would like to create, you preferentially etch out the chromium layer. So, what has been done here, you had a uniform layer of chromium all over this place, and these areas the chromium, I'm sorry, it's not working. Yeah, it's working. These areas, the chromium layer has been etched out, and that is how you make a mask. And well, of course, yeah, how do you etch out this chromium? You typically use a E-beam or a laser or an X-ray writer to strip off chromium. And we also talked that for making integrated circuits, multiple masks with multiple patterns are necessary, and that leads to the requirement of a hardware or a very big instrument, in fact, the mask aligner. I will see if time permits, I will give you some example of how a mask aligner works, but it is a huge hardware instrument, and there is no reason why we should bother much about the hardware of an instrument. So, you know that there can be something called a mask aligner is enough. I mean, that is the whole purpose of this introductory course on patterning. So, here now this slide should make sense to all of you. You should know, understand the color coding of each of these layers. So, this is the silicon wafer you started off with. Sorry. This is the silicon wafer you started off with, and then you have deposited so let's have a relook. There was a small problem with the computer, sorry about it. So, here you can see you started off with the silicon wafer, then you have grown the oxide layer. In fact, this tiny thin red layer is the priming layer. Now, you also understand that. Then you have coated the photoresist by spin coating. What is the next thing to do? You bring in the photo mask. You now, looking at the geometry, you also understand that you had started off with a chromium coated glass, and over these areas the chromium layer has been stripped off, right. And so, only this area is going to act, according to this particular figure, is going to act as transparent to opaque to the UV light, and all other areas are going to act as transparent to UV light. So, what is the next step to do? Next step to do, of course, is to you place the photo mask and then you expose, and as you expose, you can expect the photoresist. You should understand this fully now. You should expect the photoresist to change its property, and now you cannot really comment whether from this picture the color coding. Of course, in a real process you will be knowing whether you are using a negative photoresist or a positive photoresist, that is not the issue. But if I ask you from this particular schematic as to what has happened, all you can say is that upon exposure these yellow areas have changed property, and which is expected, because looking at the geometry of the mask you can say those are the areas over which the UV light came in contact with the photoresist layer, and therefore, it has changed property. And now, you also know that if you are working with a positive photoresist, in fact, these areas have strengthened, become stronger. So, if it is a positive if it is a positive, if I am working with a positive photoresist, these areas have become weaker, and with a positive photoresist the profile that you will get will be something like this. This is the remaining photoresist layer, and if you instead are using a negative photoresist, you will be getting a profile like this. So, these areas have strengthened. Of course, this you will get from here to here, there will be one more step that will be associated, and that will be the step of development. So, I think this is a good time to stop. The way I have simplified the picture, please understand that though you are learning photolithography, you are learning a very simplified picture of photolithography. It is not a simple process like this, but I have tried to deliberately keep it very simple, so that you understand and have a basic idea. Looking at this particular schematic, let us look at it again. So, here we bring in the photoresist layer. You subsequently what you do is you bring in the mask. Sorry, it is not working. So, you bring in the mask, and then you do the exposure. So, the way I have explained, as if you simply place the mask on the photoresist layer and simply do an UV exposure, but that is not often done. There are additional complexities that are there during the exposure process. So, in the next lecture I will start talking about the exposure, different exposure modes, and then we will move on to give you a glimpse of certain other very interesting developments in photolithography that has taken place, and subsequently we will also try to find out what are the limitations of photolithography, and then move on to the polymer specific soft lithography techniques. Thank you.